In this video, we will talk about circular motion. We will define the basic quantities needed to describe circular motion so that in the next video, we will be able to talk about centripetal forces and such. So the title of the video is Circular Motion. And let us start by drawing a circle since we are talking about circular motion. So this is a circle, okay? Let's say that we go from this point 1 to this point 2 along the circle. Then we can draw this radius r, and then this radius r, and I'm sorry, the radius of the circle is capital R. So if we go from 1 to 2, we cover an angle theta and an arc length of s. From basic geometry, we know that theta is simply s over r, where notice that if we were to use units for theta, then we divide meters by meters. So this is a dimensionless quantity, which we call radians, okay? So angles are measured in radians when we deal with circular motion. So a radian is a number. And when we say dimensionless, we mean that it doesn't carry any base units. So it's not meters, it's not seconds, it's not amperes, it's just a number, okay? So radian is a number used as the unit to measure angles, okay? And please always use radians, not degrees. When you work with circular motion, but also in physics in general, it's better to use radians. And the reason is simple. So remember, we just defined theta to be s over r. So s is theta over r. Okay, so assume r is 1 meter and theta is 1 radian. I'm gonna define what 1 radian corresponds to in degrees soon, but think of 1 radian as about 57 degrees, okay? So using radians, S is 1 radian times 1 meter, so that's 1 meter, which makes sense. So if an object travels along a circle of radius 1 meter, traversing an angle of 1 radian, it's going to cover a distance of 1 meter. If we convert radians to degrees, then we will multiply 57 by 1 meters, which will correspond to 57 meters, which is ridiculous. So that's why I use radians, okay? So how do we convert between radians and degrees? So if we are given an angle in degrees, we just simply multiply by pi over 180 degrees to get theta in radians. And if we are given a degree in radians, we do the reverse. So we multiply by 180 degrees over pi to get theta in degrees. And let's do 2 simple examples. So for example, 30 degrees times pi over 180 degrees gives you pi over 6 radians. So 30 degrees is pi over 6 radians. And let's do the other example. So pi thirds, for example. Pi thirds in degrees is, so we have to multiply by 180 now over pi, because pi corresponds to 180 degrees. So pi gets cancelled and we get 60 degrees. So pi over 3 is 60 degrees. Okay, simple as that. And I owe you the example of 1 radian. So 1 radian times 180 over pi radians gives you 57.3 degrees. Okay, which is what we used earlier to show why we need radians instead of degrees. Okay, now let's turn a clean page. Now define omega to be the change in angle with respect to time. You can also define it as simply theta angle over time. So this quantity is measured in radians per second and is, so define omega to be theta over t to be the angular velocity, okay? So it tells you how fast an object spins, pretty much. Okay, now recall that theta is S over R. So S is theta times R. So if we divide both sides with t, we find S over t to be theta over t times R. So we see immediately that what is distance over time? Velocity. What is theta over time? Angular velocity. So V is omega times R. When objects move along a circle, they have a linear velocity defined by their angular velocity times the radius of the circular orbit. Okay? So V is the instantaneous velocity. And it's constant in magnitude, but it changes direction all the time. So, but it constantly changes direction. How do I know that? Because V is defined as the change in distance with respect to time, right? So if I draw my circle again, okay, and this is R, okay, then an infinitesimally small change in distance corresponds to this tiny interval that I drew there. So this part of the circle, okay? So we immediately see that the velocity, if you draw a vector for the velocity, because of the definition of delta S over delta T, this vector is going to be tangent to the circle, since this is the instantaneous velocity, and it's going to be tangent to the circle at all points, meaning that if I move from this position to this position, the velocity is still going to have the same magnitude, because the magnitude is given by omega times R, okay? But the direction will change. And since the direction changes at all times, that corresponds to an acceleration. But we're going to talk about that later. So let's keep discussing about angular velocity. So by the way, in A-level physics, we deal with problems in which omega is constant. Okay, because if omega is not constant, then we will have a change in radius. Okay, but here we assume that the radius of the circular motion is fixed. The object does not accelerate in the angular direction. That's something people study at the university. Okay, so because omega is constant, then the time for each revolution will be constant. For each, sorry for the grammar if I make mistakes, by the way, for each revolution will be constant. Okay, but how much angle does the object cover in one revolution? If we go back to this circle, in one revolution, the object goes from, let's say, here all the way around to here. So that's a full circle, which corresponds to 2 pi radians or 360 degrees. So from the definition, omega is delta theta over delta t. So if we define the time for one revolution to be capital T, then omega is also equal to 2 pi over t, where this t is the period. Okay, so solving for the period will give you t equal to 2 pi over omega. So t is the period. T is the period. In physics, whenever we deal with a period, we can also define a frequency. So F is 1 over t is the frequency for the circular motion. So since omega is 2 pi over the period, then omega is also equal to 2 pi f, since f is 1 over the period. Okay? So these are some definitions that you will need in problems. And here I chose to do just the theory part in these videos. We will talk about problems once we get to solve past papers and such. So let us go back to what I told you about velocity. Velocity in circular motion is constant in magnitude, but the direction changes at all time. So let us draw this circle again. Okay. So, okay, to do this properly, you need to define an infinitesimally small angle, delta theta, and an infinitesimally small interval, delta s, etc. But this makes it complicated to understand what's going on. So we are going to assume that delta theta, we're going to draw a large angle, and we are going to assume that it corresponds to delta theta. So we are kind of gonna zoom in to this situation. So let me do a clean page. So what I'm trying to say is that we will assume that an object goes from point 1 to point 2. So this is my circle, and we will pretend that this is delta theta. Okay, we're gonna pretend that this is an infinitesimally small angle, because I want you guys to see what's going on. So this is delta s, the interval that it covers. So it corresponds to this little interval there, okay? And notice here, by the way, that delta s is so small that we can assume that it's a straight line, okay? So if an object goes from point 1 to point 2, this is the radius. So we can take this thing, which is kind of like a triangle. So if I draw a line here, I'm gonna erase that line later, okay? So if I draw a line, that line's length is delta s, okay? We're gonna pretend that. So that forms a triangle. So let me draw the triangle here. Sorry, what am I trying to do? Okay, so this is r, this is r, this is delta theta, and this is delta s, okay? So this is a triangle with both sides equal, okay? That's important. Now at point 1, the instantaneous velocity is this vector v, and at point 2, the instantaneous velocity is this vector v. So now this is actually our initial velocity vi, and this is the final velocity vf. So delta, if we revert back to using vectors, so this is vi and this is vf. Now delta v, what is delta v? Is the final velocity minus the initial velocity vector-wise. How do we subtract vectors? We just add vf plus the opposite of vi. Remember that with vectors we can just parallel transport them, right? So if I take this vector vi and put it here and draw the opposite. So minus vi is going to be this vector, okay? So this is going to be minus vi, okay? So delta v is going to be a vector that will look like this. And if you imagine this to be infinitesimally small, delta v actually points along the radius, okay? It's not obvious there because we enlarged the angle delta theta, but if we go here, you will see immediately that, so this is going to be VF, and VI is going to be slightly at an angle delta theta, okay? So it's really impossible to see, but that angle between VI and VF is delta theta. So if we draw the opposite of VI there, is going to look like this. So that's going to be minus VI, and delta V is going to be this guy, this little guy over there, delta V, which points along the radius of the circle and towards the center. Okay, that's important. So notice that immediately we can draw another triangle. Okay, so I'm pretty much drawing this triangle, or I'm drawing this situation over there. So this is going to be V, this is going to be V, and this is delta theta. So remember that VI and VF have the same magnitude. That's why here I draw VI and VF as being both V, and delta V is going to be this side of the triangle. Now, if we compare these two triangles, let's call this triangle A and triangle B. Notice that these two triangles are similar. Why? Because their sides are equal. Delta theta is the same in both. Therefore, these angles are equal in the two triangles. So they have all angles equal to each other. Okay? So A and B are similar. So A and B are similar triangles. Okay? In similar triangles, the sides are proportional to each other. In similar triangles, the sides are proportional. Okay, so delta S over delta V is going to be equal to R over V. So delta S over delta V is going to be R over V. So delta V is equal to V over R times delta S. We can divide both sides, let me use a different color, by delta T, okay? But now delta V over delta T is A. Delta V over delta T denotes acceleration. And then delta S over delta T is V again. So we get V over R times V, or A is V squared over R. So we just proved a very important result. And guys, please study these steps that I took here to prove this, because it is frequently asked in past papers. Okay, so this is what the acceleration in circular motion looks like, and this acceleration is purely due to the constant change in direction of the velocity vector. Okay, now let's do one more thing before we finish this video. Since V is omega over R, I can plug V in to get A is equal to omega squared R squared over R. So A is also omega squared times R. So depending on the situation, we will use either V squared over R or omega squared times R. And this is it for circular motion. We defined angular velocity, the relationship between linear velocity and angular velocity, and we also defined angular acceleration. And guys, this is the first time I'm gonna say this. Please like and subscribe, share these videos with anyone who might need help with A-level physics, and thank you for watching. See you in the next video.